Hi everyone. So in this video I will be discussing the objectives. I'll be pointing some things out with regards to the procedure, and I'll give you a preview of what the lab sim looks like. So this lab is called Visible Light Spec. You can call it spec for short. It's okay if you don't recognize, this particular word, the spectroscopy word. We may not have encountered it in lecture, but that's completely okay. And the reason for that is because you've learned the fundamentals about visible light and about light, electromagnetic radiation. You learned about that in the quantum mechanics and electromagnetic radiation, about electrons in that chapter, which is chapter 6 for the OpenStax book. So don't worry. This lab is a little bit more detailed, I would say, you will notice, than some of the other labs, but that's okay. We're ending off the semester almost, so I hope by this time something a little bit more advanced, you are not, intimidated by it. Like, it's okay. And as always, you can email me and I'll address any of your questions if you have any. But the procedure is very informative. It gives little descriptions of what you may be seeing, and I think that helps a lot. So overall objectives: become familiar with the visible spec and how it works. I'm just going to say visible spec because this word will make me, it will tongue twist me. I will end up not saying it right. So you'll use a simulated visible spec to find the wavelength, the max wavelength for nickel chloride, a nickel chloride solution, and then you're going to generate some curve, and you will use the standard curve to solve for some unknowns. So this lab is split into two parts, as I typically have labs, apportioned into. So part 1, generate your absorption spectrum. So here in the intro, we discussed the relationship of light absorbed or transmitted, right? So those are two different things. Absorbed is when none of the light, and it's right here, I might as well read it, when none of the light is reflected back. And this right here, this sentence is in particular about when all the wavelengths are absorbed, so that you will see a color because of that. So absorption is different from transmission. What we'll be working with here is absorption. So definitely read through this intro. This first paragraph definitely is just like a recap of what you've learned in lecture. So like I said, the principles, okay? And then we go into absorption versus color observed. So each color, that about, that we can see, that humans can see with our eyes, those correspond to a certain wavelength of absorption. And then the color you will see will be the opposite. So, and by opposite, I actually mean typically it'll be opposite on the color wheel. But I we don't need to get into that. But main idea here is there's a color that is being absorbed based off its wavelength, so you will observe a color based off of that. And this table summarizes those relationships. And right here, this paragraph above explains that. So now we get to the technique of spectroscopy. So it's a technique where we can study basically matter and light. So the spectrometer can separate light, electromagnetic radiation. We know that it's basically a fancy word of saying light, into different wavelengths, and then it has a detector that can read the intensity of the transmitted light. So here what we see is a absorption curve. So this is an important feature of the results that you gather from your spectroscopy experiments. So this absorption spectrum that you see here, it's going to be different for every single, substance. So for example, if I put DNA in a solution and I put it in a, visible speck, it would give me a curve that is unique. A curve like this, but it's going to be, different and unique in its own ways for DNA. So for nickel chloride, it's going to have its own unique absorption spectrum. And what we're essentially looking for is something called maximum absorption, which is here at the peak. So that's why you see that right there. So here, this is wavelength on the x-axis in nanometers, which corresponds to the wavelength of the particular light, right, of the electromagnetic radiation. And right here on the y-axis is absorbance. So as this number increases, there is more light being absorbed, and it reaches a max, right, a wavelength max, and at that point it can't absorb anymore, and you can see that it decreases. So there's more information that you can learn about, more background and theory, in some of the videos that I'll be linking. So I'm going to have those part of the pre-lab videos. I don't have them linked just yet. You'll see them all at once, but they'll all be there once I open up this folder. But there will be one on theory and on Beer's law, which is what we're going to be essentially doing in this lab, and then another one on how an actual spectrometer works in the lab. Videos aren't too long. Hopefully they're not too much of a pain to watch. What I recommend, and I know I haven't said this previously, I always recommend watching the videos at a faster speed. I do that for my own classes and it makes things so much easier, just so that it doesn't drag on. Okay, so that's part one. And then part two, you're creating a standard curve, and this is where Beer's law comes into place. Or comes into play, sorry. And what Beer's law has to do with is concentration and absorbance. So it relates the two. So you get an equation because of that. Beer's law is an equation. And Beer's law describes absorbance, A, doesn't have any units. C is the concentration, right there. B is the path length. It's an actual length, so typically it'll be 1 centimeter. And then E is something called molar absorptivity, and it's actually like a Greek E. I don't even know the name for it, unfortunately, right now on the top of my head, but it's like a little E, and it's unique for each material and solvent. So this is Beer's law. It relates concentration and absorption. You may see this law again if you ever take biochemistry, which is why I want to introduce it to you right now, just because I think it's useful. So this right here is a standard curve. It's an example of a standard curve. It's not your standard curve, but what it is relating is concentration to absorption. Absorbance, sorry. So you're going to use Beer's law and you're going to generate a curve like this. And we call it a curve, but it should be, like a line. But you're going to generate this type of graph for our experiment. And you can see here that I give you some background info on what corresponds to what in this line. So you can think of A equals, your molar absorptivity times your cell length times your concentration. Basically Beer's law, you can think of Beer's law like Y equals M times X, which is Y equals your slope times your X value. So in this example, the slope of a line corresponds to this portion of Beer's law, and y corresponds to absorbance, and x corresponds to concentration. So here, when you generate this line, basically this slope right there is equal to this times b. Your y here corresponds to your absorbance, and then your x, which sorry I wrote over, corresponds to your concentration. So you can see how you can relate this to Beer's law. So the power of the standard curve is that it can be used to find any concentration of a substance from any absorbance that you have. So you can have one or the other. Like you can have y and you can figure out x because you have, you know, the standard curve. Or you can have x and you can figure out y because you know the standard curve equation. So what are you going to be doing in this lab? Well, first, as always, you're going to open the lab up, click here. When you open the lab, you'll see this screen, the PhET site, and then you click it. You're going to have two panels, and hopefully you have the procedure with you right now as I'm talking. I would highly suggest actually you having this open, and I'm actually going to have it open myself while I guide you through this. Have it open so that you can follow along and know what I'm referencing. So we're on part 1. You open up the lab and you have two panels as number 2 states. Step number 2 on part 1. First panel has to do with concentrations. You can adjust the concentration up and it'll you can adjust the volume, you can add solute, and you can see how the concentration changes. The second panel is what we are interested in, which is Beer's law. So click that. Now step 2, A, B, C, D, you can see that everything available to you here in this little simulation is being described. So you have your light source here, and you can see that when I hover over it, you can see that it allows you to click. And now that I clicked it, you have light going through your solution. So this right here is your solution, and it's inside something called a cuvette. I know you probably haven't heard of that, and that's okay. All it is a little like a little tiny container, and it's typically made out of glass. So this is your sample in the cuvette, which is what step 2b is referring to. You can drag the ruler here in order to measure it, and you can see that the simulation gave you 1 centimeter automatically. But what you can do, if necessary, you can make it wider. Okay, and you can see how that's changing things up here, right? I haven't talked about this just yet, but you can see that that will adjust, your readings. Now I took it back to 1 centimeter just to take it back to default. Another thing you have here, step 2C, is a meter. This meter is, your spec, your detector. It's what actually gives you your readings. And it allows you to read in transmittance or absorbance. Remember, light can either be transmitted or absorbed. So you have those two options. And then finally, step 2D, you can overall see that you can change your solution here. We can call this our benchtop with our different solutions available in this lab. So we have drink mix, a bunch of, aqueous solutions. Nickel chloride in particular may be, hint, may be useful to us in a little bit. So you have those solutions, and you have different concentration here that you can adjust, right? And you adjust it actually through this little knob, I would say. I don't know how to describe it, but you adjust it here, see? And you can see that when you make it stronger, it turns, stronger in color when you have a higher concentration. So those are the main components of our lab sim. Oh, something, unfortunately, sorry that I forgot to mention real quick. So about the light, back to the light, step 2A, you can adjust the wavelength. So you can click variable, and then that will allow you to change it, okay? Or you can go back to preset. So that's step 2. Just understanding what is available here on the lab, I would say, is the most important thing. So take some time, as part 1, step 3 mentions and suggests, go ahead and click around for a while so that you know what's going on, you know what to click when you need to, and you know what's available to change, right? And also, if you want to just start over, just click this little circle arrow, and it'll reset everything for you. Okay, so don't be afraid to, start over if you need to. So now that I've shown you where everything is and how to adjust everything, I feel that you are prepared. Now, I know you might be looking at the procedure and saying, oh no, how am I going to do all of this? Take it step by step, okay? So, for example, step 3, it tells you, go ahead and see what everything does. When you're finished exploring, set the simulation for the following settings. Okay, so step 3A, like I said, take it one step at a time. So we're going to do step 3A together. In the benchtop, select the drop-down arrow to replace drink mix with nickel chloride. Okay. Next step. The concentration of 100 millimolar is okay. The cuvette should be filled with a green solution. So see how I kind of give you some indicators and descriptors of what you should be seeing. So just make sure that it matches, whatever you see here matches my procedure. And then step 3B in part 1, select the wavelength to variable. Start the wavelength at 780 by either clicking the arrows or dragging the bar. So you can either click the arrow this way, that way, or you can drag the bar. It's just easiest to drag it all the way down. So you drag it all the way down and you see that the wavelength is now 780. And then step 3C, set the meter to measure absorbance. So we're pretty much setting up, right? You haven't done the, measurements just yet, but we're setting up. So from there, you're gonna start the light and notice that now it's on and you are measuring absorbance, right? And just for reference, we have a 1 centimeter cuvette. So from there, what you should be doing, so that was step 4. And like I said, always take it step by step. So step 4, we switched on the light. The meter is measuring the light that's passing through the solution, right? And what I want you to think about what's going on here, like what I want you to relate it to is like when you have a glass of water, and let's say for some reason I put a flashlight up next to my glass, and assuming this is a glass of water that is like clear glass, it's not any color or anything, and you just have plain water in there. If I put a flashlight right up to my glass, light is going to come out the other way. So think of this, as an analogy. Think of this like as a flashlight, and think of this like a glass of a solution, right? And then on the other side is where you have your detector. So we are verifying in step 5 that we observe an absorbance value of 0.21. And then, it describes exactly what that absorbance value is and what the instrument is calculating for you. Now, from there, step 6 and on is where you're going to gather the data. And because, like I said, you know where to adjust everything. You know you adjust concentration right here, you know you adjust wavelength over here, and you know that you measure absorbance over here. I feel like you're ready. So I walked you through a few more steps. Now I believe in you, and I know you can get through everything else and complete this experiment. At least part 1. We'll talk about part 2 right now. So you're going to go through, collect the data that you need, take it step by step. Don't rush ahead or anything. Complete one step at a time. Okay, so before we go on to part 2, step 9 in part 1 mentions, and I'm actually going to just show it to you right here, mentions to graph the data that you collected in part 1 using Excel. So back in lab 1, you graphed measurements of bubbles, and you graph that using Excel. You are going to do that exact same process here, except now with your absorbance and your wavelengths. So where you will be measuring, or you'll be recording those measurements here, right? And then you're going to go and graph that in Excel, let you do that on your own. And then all I want here is a screenshot of the graph, or the graph itself. You can copy and paste it. So just an FYI, you learned how to graph. I am confident in everybody being able to know how to graph. I will also link a pre-lab video on graphing, the same one that I linked back then in lab 1. I will link it here to this lab. So if you need a refresher on that, just visit those videos. And that's it for part 1. Part 2, we are creating that curve that we were talking about, that standard curve. So once again, I suggest having these steps open while I discuss this. Hopefully briefly. This video is getting kind of long, so I apologize. But part 2, we're creating the curve. So you're going to return to the sim, and you are going to explore a little bit more by playing around with the simulation. So in that first part, right, where we had nickel chloride and we adjusted to 780 and we were looking at absorbance, we did not adjust, we didn't talk about the concentration at all in part 1. Okay, hopefully you noticed that. It was just different wavelengths and recording the absorption, the absorbance. I need to be more specific. The absorbance. Wow. Hopefully you're laughing at me. But you were adjusting, again, wavelength, measuring the absorbance. Those were the 2 things you were looking at in part 1. Part 2 is where we're starting to visit concentration changes, okay? And that's where Beer's law comes into play. Remember, Beer's law relates absorbance, concentration, the cell length, the cuvette length, which we know is 1 centimeter, right? But we can change it. And the little e, which is molar absorptivity, that's just a constant, okay? That's very specific, and that is not something you really need to worry about, okay? So part 2, again, number 1, I'm kind of just, step number 1, I'm kind of just trying to guide you in and, you know, explain how we're working with concentration now on top of everything else, right? So you can play around with it. You can choose different solutions, change the width, see how that changes, you know, the absorbance, right? I'm literally just changing things around, and you can see that changing the width changes the absorbance, okay? Now, you can refresh everything before you start, collecting your data. But you're going to start by selecting nickel Cl2. Once again, you are going to keep this at 1 centimeter. So I'm on step 2B right now. And then step 2C, set the wavelength to the maximum wavelength value that you found in your earlier work. So you can see how this builds on each other now. So you are going to have to use the maximum wavelength that you discovered, that you recorded earlier. And that's what you're going to set right here. Okay. Now step 2. Oops, I have step 2 twice. It should stay. It should say. And I'm going to show you where I'm at. This should be step 3. Don't know why it did that. But anyway, so step 3. That's where I'm at right now. Notice that the concentration of the solutions we're working with are given in millimolar. You are going to select first, or you're going to slide, You're going to slide the concentration to 0. That's what step 3 is instructing you to do. And then you're going to record the absorbance. So this, I just have it on a random one, right? But you were supposed to set this to the one that you determined was your max wavelength. Okay, so I have it on a random one. Don't take mine as a measurement. All right. But basically that's what you're doing. You're sliding this to 0 and measuring. That's step 3. Notice that the end of step 3 mentions continue measuring the absorbance for each 25 millimolar step until you have reached 300. So you're going to change this every 25. You're going to increase by 25 each time, or try your best. Like if it's 26, just take that measurement and then, read the absorbance. It's hard. You can't change it by number. You have to move this thing. Or, yeah, you can change it with the arrow. See, I just discovered that, or I just remembered that. And then so that would be one measurement, right? You took your 0, now you're 25, and you're going to keep going until 50. And you keep going every 25 in 25 millimolar increments until you get to 300. Okay. So that is what you are going to fill out in, this is where I was at right here, in table 2. From that information that you fill out in table 2, and let's scroll to table 2 so we can see how it looks. It's concentrations and then absorbances. So for example, we were just on 0 millimolar, right? And there was an absorbance associated with it. And then here it was 20. And then next, right, we went to 25. So here's 25. And then there was an absorbance we recorded. And you keep going until you get to 300. So you may need to add in some lines here. Not sure, but if you need to, just add it in. It's not a big deal. So that's the data that you're going to have that you are going to graph. So you're going to, once again, graph the data. So those are the skills that you learned back in lab 1. And like I said, I will be including a pre-lab video that helps you out with that. And then you're going to report all this data. So remember how I mentioned, Y is basically your A, your absorbance. M is basically this, your molar absorptivity times your cell value, which is 1 centimeter. And then X is essentially your concentration. So you're going to match it up to that because you're going to generate the equation for the line. And then that line will help you get all this information right there. Okay. So insert the graph here, and then from there, that will allow you to answer some unknowns. So let's go to those unknowns so I can explain it a little bit better. So you're going to report this, report all that information. But once you have that line, you can find these unknowns. So we know that y equals our absorbance, right? So you can plug in this y and solve for an x. Or you can plug in an x and solve for a y here, right? So whichever way you need to go, you can solve for that. So you'll show those calculations here. And then you're done with the lab sim. I know it's a lot of work, and I know this lab is a little bit more complicated, but I think it's a very good lab. You're really, recording your own measurements, and you're taking your own measurements, and it's a good technique to understand. So we're ending off this lab with some applied exercises that have to do with quantum numbers and electron configuration. So just a refresher and review, kind of relating to the same idea, the same chapter material at least, and you'll answer these questions. So just answer them in full sentences. If you need to answer, like a short answer, if I'm asking for the electron configuration, just give the electron configuration. Those types of questions. And that's it for Lab 8. As always, if you have any questions, please let me know.